Have you ever stopped to think about what the phone in your hand, the clothes you're wearing, and maybe the water bottle on your desk all have in common? Well, today, we're going to dive into the hidden science that connects pretty much everything in our modern world. It's a world built from invisible chains. Okay, so let's get specific. Think about it for a sec. A clunky, old-school telephone, a super high-tech transparent shield that can actually stop a bullet, and a soft, cozy sweater. I mean, on the surface, they could not be more different, right? But believe it or not, they all share a secret molecular identity. And the answer is polymers. That one word connects this absolutely staggering range of materials that have so completely shaped our lives. It's actually kind of hard to imagine what the world would even look like without them. You know, we tend to throw the word plastic around for all of these things, but that's really just one branch of a huge family tree. The more accurate scientific term for the whole clan is polymer. And these materials are so fundamental to society that, doing without them is pretty much unthinkable. So, what is a polymer really? How can one single basic concept be the foundation for so many radically different things? Let's break it down and get to the bottom of it. Everything, and I mean everything, starts with this little guy, the monomer. The best way to think about it is like a single Lego brick, or one paperclip, or just one single link in a chain. It's the basic, fundamental, repeating unit. And a polymer is simply what you get when you link those monomers, those single parts, together into a long, long, long chain. And we are not exaggerating here. We're talking about a true giant of the molecular world, what scientists call a macromolecule. You know what? Here's a great way to picture this. Imagine a playground just filled with kids running around. Those are our individual monomers. Then a catalyst, let's call him the drill master, shows up and yells, "Everybody link hands!" So they do, and they form this long human chain. That's our polymer. But here's the absolute key. To keep that chain going, every kid needs two free hands, one to hold on to the kid in front and one for the kid behind. In chemistry, that's called bifunctionality, and it's the real secret to making these incredibly long polymer chains. And this right here really puts the sheer scale of these things into perspective. Look at common table salt. Its molecular weight is about 58. A single polymer molecule, we're talking hundreds of thousands, sometimes over 1 million. It's not even in the same ballpark. And it's this massive size, this incredible length, that gives polymers all their amazing properties like strength, flexibility, and toughness. All right, so how do we actually build these giant chains? Well, the process is called polymerization. And as you can probably guess, chemists have a few different tricks up their sleeves to get all those monomers to link up just right. The two main routes are addition and step polymerization. Addition is this super fast, rapid-fire chain reaction. It's like linking paper clips together as fast as you possibly can. Click, click, click. Then there's step polymerization. This one's a little more methodical. It's a very deliberate step-by-step reaction where specific bits of the monomers have to connect, and sometimes they'll even spit out a tiny molecule, like a little drop of water, in the process. And get this, it's not all something we humans invented in a lab. We might think of man-made plastics, but nature was the original master polymer chemist. Cotton, silk, wool, even natural rubber, those are all natural polymers. We've just gotten really good at learning from nature's blueprint to create our own synthetic versions, like nylon and PVC. Okay, so this is where it gets really, really clever. See, it's not just about making chains, it's about designing them with purpose. By controlling a chain's length, its shape, and how it gets along with the other chains around it, scientists can literally custom build materials to have exactly the properties they want. And here is a perfect example of that. Let's talk about chain length. Chemists call it the degree of polymerization, or DP for short. And the rule of thumb is pretty simple. Just like a long rope is way stronger than a short piece of string, longer polymer chains, a higher DP, almost always create much stronger, tougher materials. That's because all those long chains get tangled up together, kind of like a big bowl of spaghetti, making them way, way harder to pull apart. Another huge design choice is how a polymer reacts to heat. On one hand, you have thermoplastics. The spaghetti analogy is perfect here. You can heat them up, they get soft and melty, and you can reshape them over and over again. But then you have thermosets. These are the one-and-done polymers. Think about cooking an egg. Once you fry it, it's set forever. That chemical change is permanent, creating a super hard and fusible material. So what does all this add up to? Well, it means that polymer chemists are basically molecular architects. They get to pick their building blocks, the monomers, and they choose the construction method to create materials with these incredible custom-made combinations of properties. And the power that gives them is, well, it's pretty mind-blowing. This quote just captures it perfectly. With polymers, we can engineer materials like polycarbonate, that's the stuff in those bulletproof shields, that combine properties you just never ever find together in nature. I mean, stop and think about that. The clarity of glass combined with the toughness of steel. That right there is the magic of polymer science. So you see, from the simplest plastic bag to the most advanced components on a spacecraft, it's all a story about chains. It's a story of designing and building, one molecule at a time. And that leaves us with a really fascinating question. As we get better and better at being these architects of molecules, what seemingly impossible materials are waiting for us just over the horizon? What will we build next?